You thought you put the graduated calendar interesting nothing. You were spending more every other the basis of this class. Storm drain. Okay. All right, in your lab book, what I want you to do is to describe how you created the siphon using both pictures and words. Okay? We'll take some time right now to do that. How did you create the siphon? Use both pictures and words to explain. Let me give you one more minute. Okay, so this is actually a pretty useful skill to have. Anytime you want to drain something, siphons are usually a very easy way to try to do that. I think a lot of people do it wrong, or at least they're not wrong, but in an unsanitary way by using their mouth like a straw. But imagine if you're having to drain a liquid that you don't really want in your mouth, right? So there is ways to do it without having to use your mouth. And that way is getting fluid in the tube. Okay, you want as much fluid in the tube as you can before you start the siphoning. The second condition that has to be met is that the draining tube has to be what compared to where the original tube is? Lower. Yeah. So this pressure along this line right here, let's call this P2, would be what to the pressure along this line, which we could call P1? Higher. Mm-hmm. Okay. So you're saying this is higher? P2? Mm-hmm. Why? What makes it higher? Okay, remember, which way you look at it doesn't matter. More height or more depth, right? So remember, everything along this line has to have the same pressure, right? So because that line has a greater depth over here, it would have a greater pressure over here. Okay? But then that should start to cause a little bit of a uncertainty or questioning in your head. Okay? Which way does the fluid go? Up? Down? Both? Out of what? Out of the tube. Which end?
The higher pressure.
The higher pressure?
On the side of the...
If there's higher pressure here, why is fluid flowing towards that point? What is this local minimum? Well, with a siphon, you can't look at it in terms of just the liquid. You have to also analyze the other thing that's there that we always kind of neglect because we can't see it, which is what? Mm-hmm. And so what's occurring right here? Mm-hmm. Okay, atmospheric pressure, right? Okay, but what's also occurring down here? Atmospheric pressure. Okay, it's all over, wherever the air is, right? Okay, do you remember what atmospheric pressure was in terms of the number? Yeah. Okay, so we can do all three units if we wanted to. We can do pascals, ATMs, PSI, whatever we want, right? Okay. Just because we don't often do it, I'm going to do PSI. But remember, you don't have to memorize that. Okay. So the atmospheric pressure is 14.5 psi, both locations. Now, inside the liquid, I don't know exactly what it is, but I do know it's going to be something less. Okay, it's not going to be as strong as atmosphere because otherwise it wouldn't stay in the cup. It would explode out of it, right? So I'm just going to keep it simple and just say, I don't know, maybe 1 psi here. And we said this is what, higher or lower?
Higher pressure.
So I'm just going to make it up and say 2 psi here. So I haven't broken any rules. But I can now use these numbers to help me figure it out. Sometimes numbers make it a little easier. So, what do you notice about the top part where the hose is and the bottom part? What do you mean the pressure is greater? Okay, so the net pressure, you mean like the difference between the two? Where is it greater? Where?
On the outside.
So the net pressure is greater here? the bottom? What would be the net pressure at the bottom? What would it be?
Oh,
12.5.
Why is subtracting them better than adding them? Yeah.
Because isn't the atmospheric pressure pushing the water across? Yeah.
Right. So they're fighting each other, right? They're going against each other. Liquid's trying to push outwards, the air is trying to push inwards, right? So you want to think subtraction, not addition. And if you think subtraction, then the net pressure down at the bottom is what compared to the net pressure up at the top? Yeah. So up here we're going to have high net pressure, and down here we're going to have low net pressure. One of the fundamental things about fluids in motion, which is really going to be our focus for the rest of this week, okay, it's our last little part about fluids, is that fluids will always flow from regions of high net pressure to low net pressure. But you got to think of it in terms of the net pressure. Okay, if it's just within a pipe, you can just look at the fluid. But anytime it exits a pipe or interacts with the air, you get to also account for the air. Okay? So fluid flows from the high to the low. Now we only created this lower net pressure by increasing the pressure of the liquid. Just kind of a backwards thought, right? We're increasing pressure to decrease net pressure. Okay? And we only achieve that by making sure this is what compared to this?
Lower.
Yeah. So there's really two conditions for a siphon. We want continuous fluid so that we don't introduce air pressure anywhere else, right? But we also want the end to always be lower than this, right? Okay, and sometimes you're limited by, as y'all saw, how long your tube was, or something like that. Okay? But that's it. That's how you create a siphon. Okay, continuous liquid, and then one end lower than the other. Yeah.
So since the water's going up, does that mean that there's actually a depth on the water surface?
There's a depth on the water surface?
Yeah. Does that mean that we consider the water surface to have depth since the water's going up and there's a new height going in the water?
Well, I mean, depth, it's kind of like height. So, someone asks you how tall you are, that's making an assumption just right there. What are you assuming? Yeah, or above the bottom of your shoes or feet, right? So you're setting a 0. So same thing here. We can set a 0 wherever we want. And so you could always think of the surface as having depth if you want, but you don't have to. It's more important what's the difference between any two locations. Okay, same thing with height. All right? So that's how a siphon works. If you ever had a fish tank, this is the easiest way to drain the fish tank. Right? I'm picking it up. Yeah.
Is there any situation where you add the atmospheric and the water pressure? You always use it.
Any situation.
Like in the general rule, just like subtract.
If there was a third object you were considering, whether it was a fluid or maybe the container, then both the water and the atmosphere are pushing the same direction at certain locations, like the bottom of the container, right? So, but for fluids, no, I can't think of one.
Okay.
Yeah.
Wait, so if you said that the two is at the bottom, so then in the container, it would be a pressure of 16.5 psi on the container?
No.
So what would it would still be pressure inside?
Well, on the container is a little more problematic. Like if I zoomed into this, wait, you mean in the container or
Yeah,
in
the
tube?
water in the container,
Water in here?
yeah, combined with the pressure of the atmosphere, would it 1.5 or?
No. So, how to describe that? So, pressure is any force divided by area. So if you just imagine the fluid as a single object, then what things are acting on that object? You've got air, you've got gravity, you've got this container, and even a small part, maybe the tube is exerting a pressure on it too, as a reaction to its pressure on it. And so you would have to factor all those in, okay, if you really wanted to describe the pressure on the fluid. Or you could think of the fluid as individual molecules, and then every single molecule, think of force diagrams on every single molecule, okay? But what the question you need to ask yourself is, what would be the benefit of that analysis? What could you do with that information? Okay? Well, exactly. All right? But yeah, you're not gonna have to worry about that too much. Okay? But we are going to eventually, someone brought up energy. Okay, we are gonna tie this to energy tomorrow. It'll be our very last topic. But for now, all I want to really focus on is pressure, and the next thing, which will be speed. Okay? The atmospheric what? No. Atmospheric pressure can be exerted in any direction that there's atmosphere. Like on your table, it's down on the table, it's underneath your table, it's on the sides.
In the water, case of the water, so that's like attractive.
It's pushing up here,
Yeah.
but over here it's pushing down, right? Okay. All right. So this is actually, what is this a picture of? Do you know? A car. What else do you see? Ah, see some lines? Okay. Yeah. So this was taken inside of what's called a wind tunnel, right? And since we can't see air, what they do is pipe in smoke. Okay. Over on the right side would be regions of high pressure, right? That's why it's kind of thicker there, and then you can see it's starting to fade away because pressure decreased. But more importantly is why would they do this? Why do we want to see the air? Why would we put the car in a fancy tunnel like this and do this? Do what? Okay, you can use fancy word about aerodynamics, but what is that really looking at? Okay, stress. Do you know what stress is?
Like the pressure that, like, how much an object can take? Isn't that like a pressure an object can take?
Yeah, we never learned about stress and strain. It's not part of AP Physics, but it is part of physics. If you ever get into engineering, you'll definitely learn the difference. Okay? But more importantly, if we try to relate it back to AP1, okay, what causes something to slow down as it's moving? Friction. But friction is not just from the ground, it's also from air. Last year we called that drag, right? That's the aerodynamic term. And so you're kind of looking at drag here, right? But more importantly, why I brought this up is what this shows you is up here, if you notice the very top lines don't really curve very much. There's a slight curvature here, okay? But for the most part, they're straight, okay? Over here, this is where you're getting the drag, right? And so what do you notice is true, or what are these lines showing you? They're showing you where the drag is. They're showing you almost what the speed is, all that kind of stuff. Okay? Now there's a problem with gases that we don't have with liquids, which is what? Yeah, compressibility. So this isn't exactly analogous to what we're going to talk about because of the compressibility. Okay? But at the same time, I've showed you this picture because with fluids, it's helpful to think about lines like this, even if they don't show you them, but only when fluids are in what? Yeah, which again is our topic for today. So here's a pipe, and if you notice, they've drawn lines for you, which they won't always do, but these lines can be considered the same type of lines. We call them streamlines. Okay? And if you notice, the lines start out widely spaced, and then they become closer, right? And what do you think is the reason for that? What do you think might be the consequence of that? That when you take a fluid and flow it in a pipe, and that pipe suddenly gets narrower, do you know what happens to it? Okay, so you can maybe say higher pressure. Okay, but you have to be a little careful with that. Because if I do what I was doing before, if I do a straight line all the way across, what's true about the pressure on that line? At least due to depth, right? So we'll come back and look at pressure more tomorrow. But for right now, I want to focus on two things. I want to focus on really, well, three things. Area, distance, and then this V, you have to be careful because V can be volume or velocity. Here, because it's represented by a vector, it's velocity, right? So that one right there is velocity. Okay. All right. So what I want you to do, if you have room, copy this. We're going to write a little bit after this. If you want to go to the next page, it's totally fine, but copy this picture down into your lab book. Okay, now trying to connect this to our siphon activity, the reason why we did the siphon activity was to kind of connect what we had talked about before, maybe pressure at depth, with what we're going to start talking about, which is fluids in motion. So without even seeing the rest of this structure, where do we know higher pressure is? Yeah. So somewhere over here would be a higher pressure over here, right? And then somewhere way over here would be a lower pressure, because fluids always flow from high to low pressure. So again, without even seeing anything, I know that's true, but that's not really our focus, okay? That's just the cause. The cause is some sort of differential pressure that's allowing fluid to flow, causing fluid to flow. But now that fluid is flowing, we want to kind of analyze what happens when you change something like the area that it's allowed to flow through. All right? So what they've done is they've shaded two regions, right, of the fluid. This whole thing contains fluid, right? But these two regions right here are our focus. And what we're going to say is that the volume of this first shaded region on the left side is equal to the volume of the shaded region on the right side. Okay, they don't have to be. We're just shading regions that are equal volume. Does that make sense? Okay. Since they're equal volume, what I can start to do is use some of these variables they've given to begin to write more detailed equations. So how could I calculate volume using what they've drawn in the diagram? Yeah, volume is what? Area times? Yep. So for volume, I can say A1 times delta X1 equals A2 times delta X2. Okay, I'm just replacing volume with area times the length. Okay? Now, let's try to pull velocity into it. What do we know is our definition for average velocity? Yeah, so this is going to equal delta x over delta t, right? If I rearrange this equation, then delta x equals what? Velocity times time. So I can come down here and replace my delta x with velocity. Okay, I kind of do a curvy v, a cursive v, to separate it from volume. But however you want to do it, you can always write out the word if you're really worried about it. Okay. And we'll set that equal to the second one. And if you notice, what's on both sides that can be canceled out? Mm-hmm. Okay. Delta T goes away. And you're left with what's called the equation for continuity, where A1 times V1 would equal A2 times V2. But you have to remember that that is velocity and not volume. Okay, but that equation's on your AP formula chart. And out to the side of the equations on the formula chart, they tell you what every variable is. So you just need to take the time to look if you forget. Okay, but this is actually a concept you probably knew before you came to class today. Okay, because you've all done stuff like take a hose and put your thumb over the end of the hose, and what happens to the water coming out of the hose? Yeah. Or why did the water come out so fast out of these nozzles compared to, say, the sink you have at home? It's not the pressure, because we're about the same depth underneath the water tower as your sink at home, right? So then why does it come out so much faster here? Yeah, because we've reduced the area that the water exits at, right? So the smaller area means a what velocity? Okay, so it's not necessarily a greater pressure, okay? It has to do with a smaller area. All right? Make sense? So that's continuity. Now, there is one extension to this. You can use this equation not only to solve for areas and velocities, if you know 3 of the 4, right? But there's another thing they ask for that's connected to this. It's called flow rate. Okay. So the flow rate of a fluid is going to be the volume divided by the time. So it's the volume per second. How much fluid is passing a point in a second? Okay? In college, we use the variable capital Q for this, but the AP doesn't, so we won't. Okay? So you just have to know the definition of it if you want to solve for it. Okay? But how does it connect to this? Well, what are the units for this? So if I take a meter cubed and divide it by a second, I would have my units for flow rate, right? Well, I could take this and split it up into meters squared times a meter per second, which is what times what? Okay, so this flow rate also equals area times velocity. Okay, either one of those will get you the flow rate. You can do volume per second, or you can do area times velocity. Okay, so what is this equation saying about the flow rate in this picture? Yeah, so the flow rate is going to stay constant. The individual area and velocities can change, but the volume per second is going to stay the same, as long as whatever is creating it stays the same, the difference in pressure. Okay? Yep.
So A1 times B1 would be equal to A2 times B2, which would also be equal to the volume of the time.
Yep. Okay. Make sense? Alright, so you'll get questions about flow rate, you'll have to solve for it different ways and that kind of stuff. Alright, now, there is a part of this that we're limited on how deeply we can get into them, because this starts to require calculus, okay? If you notice, what this is really saying is what's true about the velocity between here and here? Yeah, it's constant, because the what's constant? Okay? Well, what about between here and here? Is the area changing?
Yeah.
If the area is changing, then what else is changing? Yeah, and so when you're getting constant change, calculus is required, so we won't worry about that section, really, okay?
Are you a spirited individual interested in getting involved, supporting the other student groups here at Tompkins? If so, please see Coach Wagner in room 2019 and apply to be Mr. T, Falcon mascot. Please see Coach Wagner in room 2019 by this Friday for information.
Hey Falcons, are you interested in science and love to compete? If so, join the OTHS Science Olympiad team. Science Olympiad is a competition where teams compete in events from various fields of science, travel to tournaments, and win medals. For details on how to join, attend an informational meeting in Mid-Constitution 2322. They will be held before and after school today, Wednesday, September 1st, and Friday, September 3rd.
Congrats to varsity volleyball defeating Austin last night. What a huge match! Also, congrats to freshman B as they beat Citgo Ranch last night. Keep grinding, FA and JP.
Be sure